Well, so let's just start by reviewing the communication part first. So in this talk, I guess we will be looking at several communication models, including the deterministic communication.
Right, double that size.
Double that size, okay. Okay.
Thank you.
Yeah, so the deterministic communication model, and here we are just focus on like two-party case. We don't worry about multi-party communication. And the function we think it's from some domain and maps to -1 and 1. And in fact, sometimes like if we are working with and or these things that we are familiar with, we'll talk about 0 and 1 instead of -1, 1. So I hope you won't be confused. Okay. So in the deterministic case, Alice and Bob, they try to solve some function together. They just communicate deterministically, meaning that whenever one party wants to send a message, that message is deterministically decided by the input and the past messages. Okay, so like in the end of the protocol, Alice and Bob should output the exact value of the function on all inputs. Well, the next model is the randomized communication model. So here, Alice and Bob will have randomness, and it doesn't matter whether they have public randomness or private randomness. But in this talk, let's say the random source is private. And in the end of the protocol, Alice and Bob should output the right answer with probability at least like 2/3 any constant greater than half. Let's say like 0.99. Okay. And similarly, we can talk about quantum communication model. So Alice and Bob can share quantum entanglement, and they communicate by sending qubits. Like the reason that I put these together is because the lower bound technique will be the same. Yeah, so we don't need to like worry too much like what exactly is quantum communication model. And finally, another model is the unbounded-error communication model. And it's just like the randomized model. So Alice and Bob will have their own private random source. But in the end of the protocol, they only need to output the correct value with probability anything greater than half. So it does not need to be a constant greater than half. It could be like half plus 1/n. It could be half plus 2 to the minus n. So anything greater than half. Okay. So that's the communication model. And now let's talk about the lower bound technique for these models. I think we all know that for deterministic model, the rank of the communication matrix By communication matrix, I mean associated with function f is just the matrix like on the xy entry, just be the value of our function. And the rank of this communication matrix is upper bounded by 2 times the deterministic communication complexity of the function. And Tony has explained this is because the communication protocol will partition the communication matrix into at most 2 to the cost of this protocol number of matrices. Each submatrix is a rank 1 matrix, and by the subactivity of matrix rank, we got this. So this is first observed by Malho and Schmidt. And for the randomized model, we have related notion called approximate rank. The approximate rank of a matrix is defined to be the minimum rank of a matrix such that it pointwise approximates the original matrix. Is this clear? Okay. Good. And yes, you would see what's gonna come is that the approximate rank of a matrix, of the communication matrix, is upper bounded by 2 to the randomized communication complexity of the function. And maybe let's quickly see why is this the case. So whenever you have a randomized protocol, you have a protocol tree. So like in the beginning, Alice will need to send something, and she will send like maybe 0 with probability, like depending only on the node corresponding to the past transcript, the past message. And with the remaining probability, she will send 1 to Bob. And similarly for Bob, on this node, he can send like 0 with some probability and send 1 with the remaining probability, and so on, until they reach the end of the protocol. And the end of the protocol, they will output a value. Maybe it's -1, maybe it's a 1. So what is the expected value of the outputs for this protocol? Over Alice and Bob's randomness. That is just like sum over all of these. And look at the output of that leaf times the probability of reaching that leaf. And that is just by taking products of all the values on these edges. And just notice that these values for Alice and for Bob, these are independent of each other. So therefore, you can just write the number associated with input x for Alice for this leaf times a number associated with input for Bob and for this leaf. Any question? Okay. Okay. Good. So this gives us a matrix, and because if the protocol is correct to randomize the protocol, it will output the correct value, like with large probability. Then the expected value should also be close to the correct answer with high probability. The expected value will be close to the correct answer. So what we can write is this matrix, maybe like A is just this minus the communication matrix is like less than some small number, epsilon. So therefore, this is a matrix that approximates the communication matrix. And this thing is just like a rank decomposition. It tells us that the rank of A is at most 2 to the number of leads, that is 2 to the randomized communication complexity of this function. Any questions? Okay. Okay, so the final thing, the bounded error communication complexity and the corresponding matrix measure is the sign rank. And it is defined to be the minimum rank of a matrix that like agrees with the communication matrix inside. And the same argument here will tell us that the sign rank is at most due to the unbounded error communication complexity. So this is due to Pachuri and Simon. And in fact, they show that the log sign rank exactly captures the unbounded error communication complexity. So maybe I'll skip that. For approximate rank, the log approximate rank can be exponentially smaller than the randomized communication complexity. And this thing, so this also holds for the quantum communication complexity, and the exponential separation is also there. And now for the deterministic case,
Like we were saying that it was open for a long time. Most people thought that this called the log approximate rank conjecture was true. In other words, they thought that those two were polynomially related.
Yes.
That was disproved.
Yes.
A few years ago.
Yes, like just like maybe 2-3 years ago. Maybe I could mention give some credits. So for the randomized case, this separation is exhibited by Charabate, Monday, and Sharif. For the quantum case, it's proved by two groups of people. The first group is like Sinha, the Wolf. The second is Anshu, Badu, and Chate. I don't know how to pronounce his name, sorry. Yeah, and of course for the deterministic case, it's the big old problem, the real log rank conjecture. So nobody know how to handle it. So that's the situation with these lower bound techniques. Any questions? Okay, good. Okay. So this is the communication part, and the title is polynomial method. So there is the polynomial part, and the polynomial part is actually here, because I want to keep it here.
Yeah, but they
Let me see.
Maybe you can write on the underneath if you want to keep.
That's not
The last one does not.
That's not good. Yeah, for the polynomial part, not much to say. So what we are interested in suppose we have like a polynomial. Suppose we have a function. We will be interested in its degree. And we all know what's degree. And the approximate degree, well, that's just the minimum degree of a polynomial that point-wise approximate f on the boolean cube. And threshold degree, it has many names, but let's call it threshold degree, is the minimum degree of a polynomial that agrees f inside on the boolean cube. Yeah. So I think these are clear. And okay, so now the topic or the goal of this lecture is to transfer the hardness of this measure into the hardness of the rank. And then we get the hardness on the corresponding communication model. So like if you give me a function that has large degree, then I will get a new function communication matrix whose rank is exponentially large. Okay. Yeah.
Making sure I get it. So if you're going through rank, so this means that in the randomized model, we don't hope this to be tight, right?
Well, no, we don't expect it to be tight, but I don't exact. So we don't expect like from this we get like really. I mean, like, how should I explain it? Okay, so maybe I should explain it in the following way. So it's really a challenging task to find like communication problems that is hard, and to prove, for example, to prove like randomized communication complexity, to prove quantum communication complexity. Those are very challenging tasks. To find like hard instances, explicit hard instances are very hard. And using this method, it's like we can just take a hard function for these polynomials, like it's much easier task, and we automatically get a hard instance for the corresponding communication model. Yeah, so that's the purpose. It's not like we are trying to, I don't know.
You're not trying to outperform rank, you're trying to analyze something that might be more amenable to analysis and then bound the rank and then bound the communication.
Yeah, so we are not trying to like give communication lower bound for specific functions, but we are trying to find a generic way to prove to show like a complex communication problems. Okay.
Just a little background. So this is now called lifting, and it's, I think, Sherstov. This form of it is seminal work by Sherstov, where he kind of lifts these degree measures to rank measures. There's also early work by like Razborov-Sherstov that lift like decision tree complexity to deterministic communication, and now there's like a whole bunch of other versions. Yeah, the idea is to get really close upper and lower bounds for communication problems that are a little bit maybe unnatural, but but the nice thing is you can just focus on this weaker degree measure, and then you automatically, the results automatically transfer over.
Yes. Yes. So sometimes these actually help us to prove like tight communication lower bounds for, say, disjointness functions. So those like well-studied functions, but that's not the purpose. Okay, so let's just start from the deterministic case. So the deterministic case, as Tony just commented, that actually Tony and Goose and Watson, they built on the work of Raz and McKenzie. They proved a lifting theorem from query complexity to communication complexity. And we know that degree is a lower bound for query complexity. So in that sense, the lifting here is not that exciting, but there is some good part here. Let me just state what we're going to prove. So what we're going to show is there exists a Gadget function on just 6 bits. And such that for any function f, if you compose it with this gadget, then the deterministic communication complexity is at least the degree of the function. So in reality, what we prove is rank of the communication matrix is like exponential on the degree. And the good part about this result is the gadget is of constant size. So like maybe for later we will see why constant size gadget is good. And the constant size gadget is not known for like lifting theorems for query complexity. So now let me just show you.
Yeah.
By compose, you mean that
Okay.
the bits become
Well,
becomes a
okay.
gadget.
Okay, yes. By composing, yes. Yeah, by composing, I mean, like it's defined as f like g small dx2 y2. And xn and xi is like 3 bits, yi is 3 bits.
Yeah, can I just add one thing? So I think there's all this old work that tells us that like degree and decision tree complexity and that they're all polynomially related. So we do have kind of lifting theorems for query complexity, but
Yes.
it's only for Boolean functions.
Yes,
So some of the later work wanted lifting theorems, even when it was a search problem or a partial function. So
yes, yes,
that's where the size of the gadget.
yes, yes. Yes, yes, and also another thing is degree can be polynomial smaller than deterministic query complexity. So in that sense, it's weaker
Yeah, it's
also.
not quite as tight, yeah.
Okay. Yeah, so the proof, so let's see the first component in the proof. It's something that's like well known in communication community. That is, if you take a function and if you take composition with 2-bit XOR, so 1 bit from Alice, 1 bit from Bob, then this communication matrix has very good properties. In particular, it has eigenvector Ks. The characteristic, yeah, maybe let me just write it down. It's just this thing on X is just the product of the variables in S. And the eigenvalue, the corresponding eigenvalue is, maybe you guessed, the Fourier coefficient of F and times some normalization term. That is 2 to the n. N is the dimension of your function F. And if you haven't seen this before, maybe it's worthwhile to show you once. It's really easy. You just try to multiply this matrix with this vector. And see its value on X, for example. That is, like, take the sum of the Y and take the entry-wise XOR times Ks Y. And then take the Fourier expansion of F. And if we focus on these two, and we put the sum into here, then we know that the characters form orthogonal basis. So for t not equal to s, the sum is 0, and for t equals to s, we get 2 to the n. So that's f hat s 2 to the X. Okay. Okay. So up to this point, if what we see is that we got, if we just composite our original function with XOR, then the rank of the communication matrix will be the sparsity of the function f, the polynomial f. Sparsity is the number of non-zero Fourier coefficients. But that's not what we want exactly. So what do we do? Well, we can just compose f with another function to make sure the highest order term expand out into a lot of terms. There are a lot of choice you can choose, but we are going to choose this function. I call it KP. It is function on 3 bits, UVW, and it equals to 1 minus W over 2 times U plus 1 plus W over 2 times U. So if W is 1, then it outputs V. If W is minus 1, it outputs U. So this is just the index function or the address function, the smallest those functions. But here I call it KP because like Ross and Hadlock are the first to use this gadget in a related work. So just to give them the credit.
What did they do? What did they prove with this gadget?
Oh no, so they are in a setting very similar to approximate rank. Yeah, but they are working with different things. Like for deterministic case, like you have a lot of different choice of the functions, but we just use this one because it's the one that we will use later. And let's see if we compose f with this function, what happens. So we just look at each factor, what happens to each factor. Now each variable is replaced by this gadget. And we can expand this. And let's put like 2 to the minus s here. And then let's just write t, any subset of s, and chi t, and chi s, set minus t, v, and the other things. The way to write it this way is just to make sure that you can see what is happening. So like each term on f now becomes exponentially many term here, and there is no cancellation. So between different terms that from f, when it expands out into more terms, those terms, they don't cancel out. Because here there's no constant term. Yeah. Yes. So when we take this product, we just take something from here, something from here, and that give us chi t on u or chi s set minus t on b, and the other things. And just by looking at these parts, you know that there's no cancellations for the terms coming from like chi s from f, or like chi t from F. Is this? Okay. So we conclude the sparsity of the new composition is like at least 2 to the degree, maybe actually 2 to the 2 times degree of the function f. And therefore, the rank of the matrix is also this number.
There is KP or another gadget?
So this is KP. This is G. G is KP composed with XOR.
Oh, okay.
Question. Is this clear?
So composing the XOR would mean that both U, V, and W, each of them is the XOR of 2 bits, right?
Yes. Yes. So here we have 3 variables for this. And when we compose with the parity, then we have like 3, that's 6 bits. Well, I think so. The idea is simple. Like from this composition, f composed with the parity function, the 2 bits XOR function. We know that the rank of the corresponding communication problem is just the sparsity of the original function f. That's already very good, but we want the rank to be related to degree. So we want like any function has large degree to also has large sparsity. To do so, we just compose our function with some other gadget. In particular, we just take this gadget. And when we take this gadget, like if we look at any term in the original polynomial, that term will expand out into into exponentially many terms. Yes. Okay. So let's move on. Okay. So the next one, we just move on to lift the approximate degree to the randomized communication complexity. And the gadget is the same. So what we are going to prove is randomized communication complexity is lower bounded by the approximate degree. Here, let's be careful with the error parameter. So let's say this is epsilon, and let's say here's delta. Delta will be something smaller than epsilon. And we will see why we need this. Okay. Oh, yeah, okay. So G will be from on G will just be this KP function composed with the 2 bits XOR function.
The same as here.
Yeah. We don't change anything. So
If we didn't compose KP with XOR. What would you get?
Oh, no. So if we,
Still get-
so here we just get, so here we get a new polynomial. We are not getting a point, we are not getting a communication problem. And when we compose it with the 2 bits parity function, we get the communication problem. So we distribute like X and Y for the parity function to X, to Alice and Bob. But here, this we just think of it as some polynomial f. But this polynomial will have large
I
sparsity.
misunderstood what's going on. Now I understand.
Oh, okay.
I thought you were component-wise. Sorry, what happens when you do component-wise? With this KP?
No, f is a single function.
Right, f is a single function. It has n variables, I see.
Yes.
Yes.
Now let's, instead of doing,
So first you compose with KP, meaning that now it becomes 3 n variables.
right, but let's say instead, I did the same thing we did with the XOR with KP. So,
Oh, you want to do f,
yeah,
compose with XOR and then KP?
no XOR. I want to do f, each variable of X turns into KP on.
Yeah, no, but that's what I was saying. So
Oh,
it-
sorry.
when you compose with KP, it becomes a function of 3 n bits, right?
Yes. Well,
KP gets 3 bits, right? Yeah,
oh, yeah, KP, yeah, sorry, yeah.
but still not the communication complexity per se, because it's just 3 n bits. You don't even say who's
Yeah, I
Alice,
guess I
who's
don't know who's
Bob.
getting what, yeah. So I was assuming one guy would get you, another guy would get,
Yeah, I see the confusion.
one guy would get
Yes.
the point here, another negative value, I don't know which is which.
I mean, you could turn it into a 3-party
No, no,
communication
what
complexity.
two-part- what two-part?
Yeah.
Yes. So this is our new f. This is our new f. And we will compose this thing with the parity function.
Yeah,
And
but I mean, you could think of you're interested in like the query complexity of that temporarily because you're trying to compare with
yeah.
degree, and then you compose
Yes.
that sort of very
Yes. Yeah. And that also makes sense.
But I could think of this by itself as a communication problem, right? Where one player has,
Well,
That I agree. You are right. I mean,
decide how you can.
well, like this is just like the index gadget one person.
yes. I see.
Yeah,
So I see that's why it's confusing. Okay.
Yeah.
Okay. So okay. So I shouldn't. So I guess that's the reason why we shouldn't call it index
No,
function.
no, it's okay. I liked it. I liked what it is.
And then, but you still would have to decide what else gets and what Bob gets.
Right, so what I would propose is, the way you described it is, if, I forget how you said it, if,
Mhm.
so depending on the value in U and V, well, it's, yeah, which is which here? So W is,
W is the one that decides. So if W is
yeah,
one,
so
then
Bob is gonna get U and V, and Alice is gonna get W.
I
And
see.
so W is gonna
Mhm.
decide whether it
Mhm.
went to U or to V.
I see.
So what happens there?
Okay. So it actually makes sense. That's what Sherstov did.
Yeah.
So by doing that, you get like a 4 bits gadget.
Right, that's what I'm saying, it wasn't, he had an
So
extra
it
bit,
will work.
but not with the 3, right?
No, not with 3. We still need some parity thing.
Yeah.
We still need some parity. Yeah, if with 3 bits works, then we already get.
So it's known that this doesn't work?
No, well, at least I don't know how. Yeah. But I like prefer this construction because it's.
So it becomes a bit annoying because the inputs are of different lengths now, but.
Okay, anyways.
Yeah, because I think every step here is self-motivated. Like this part, like composing with XOR is something that people do, and then we immediately get a relation between rank and sparsity. And from sparsity, if we want to do for degree, then we need to make sure.
And I agree from presentation purposes, it's a nice,
Okay. Yeah. Okay. So let me just say this is due to Sherstov, but using different gadgets. And for this proof, we need some more tools. In particular, we need like a dual characterization for the approximate degree. So like if the approximate degree of your function is greater than d, that means there's no solution to the following linear program. So sum over like AS KS for all factors of order less or equal to d. So that's considering all possible low degree polynomials minus f, the pointwise approximate f with error parameter delta. So AS is the variables. And if there's no solution by LP duality, there should exist a witness. In particular, it's something looks like a function from the boolean cube to reals such that we normalize this thing. So, so we make sure the sum of the absolute values of our function phi is 1. And the inner product of the function and the witness phi will be greater than delta. And finally, this phi will have no low degree component. Yeah, so we were not like carry out the exact step here. Just take this as a fact. And let's see why this dual characterization is helpful. I guess the idea is that here we have a witness showing that the degree is large. So we may hope that we have a witness that's showing the approximate rank for the limited function is large. And the natural thing is let's consider the lifted witness. And I'll just list some properties of this object. So first,
Can you repeat what you mean by lifted? I know what you mean, but I'm not sure.
yeah. I mean exactly this thing. So phi is a polynomial. You can compose it with our gadget, and that is that gives us a matrix. Yeah. So we will use this as a witness to showing that the approximate rank of like F composed with G is large. But first, let me just list some properties of this matrix. The first thing is we can take inner product with F composed with G. And this thing, we can compute it. It's just taking sum of all the inputs for the original function f or small f. And taking the product. And these things actually appears multiple times on the matrix. So we just add up the number of appearance. That's like how many xy if we plug into G equals to that here. I'm just trying to group the entries of the matrix based on their values of the original function. And then we just times the number of pyramids for those values. Now for each z, like if we focus on one coordinate, like when we fix the output of the KP function, it's like reduced the number of possible assignment by half. So that corresponds to like 2 to the, actually 4 possible assignment for each. So if we say KP outputs 0, then we have 4 possible ways to assign WUV to make that output. And once we get that, and once we fix UVW, then there are 8 ways to fix the parity bits. That's for one coordinate. There are n coordinates. So it's 2 to the 5n. And this thing, the inner product, just by properties of the dual object, is greater than delta. So this thing is greater than delta times 2 to the 5n. This is the first property. And second, we can consider the sum of all the entries of this matrix in absolute values. And that is just like put 1 here, put an absolute value here. And we know it's 1. And here it's 2 to the 5n. So this is 2 to the 5n. And finally, the most important thing is we actually understand the spectral norm of this matrix very well. I hope we can still see it. Okay. So we know that when we compose with the parity function, the eigenvalues are just the largest Fourier coefficient of this function be composed with the KP function. And for V composed with the KP function, it's max over all the Fourier coefficient for V. And for each term of V, like we expand it into like, I see, sorry. This here is no over 2. We expand it out into this thing. We get 2 to the minus the order of the coefficient of the Fourier coefficient of the Fourier character. So here is like 2 to the minus s. That comes from here. Everything like expand out, it will be 1 on the coefficient. And then there is like this normalization factor that's 2 to the dimension of the function 3n. Okay. And then because we know like sum of phi is 1, this thing is upper bounded by 2 to the minus n. The Fourier coefficient is just the expected value of the sum is of the values. So it's at most 2 to the minus n. So the entire thing is at most 2 to the approximate degree of the function times 2 to the 2n. This is because for any character whose order is less than the threshold degree, then they are 0. Yeah, so that's how we get an upper bound for the spectrum law. Is this clear? So Leo, which part are you looking at?
Okay. You can go.
Okay. Okay, so these are the pieces that we need. And let's see how we're going to use it. So just suppose we have a matrix that approximates the communication matrix. And then we are going to consider the inner product between this approximating matrix and this witness. matrix. So I claim this C must be large. Just because I can write M as like MF composed with G minus something like something entry-wise smaller than epsilon. And this thing we already wrote here. It's at least delta times 2 to the 5n. And this, we said it's epsilon 2 to the 5n. So delta minus epsilon times 2 to the 5n. And on the other hand, if M has low rank, we can show this inner product must be small. Why? So it just uses some like matrix analytic tools. So when you take the inner product of two matrices, it's upper bounded by the spectral norm of one matrix times the trace norm of the other matrix. So the spectral norm is just the largest singular value. The trace norm is sum of all the singular values. Yeah, I think here we all know that. Okay. And when we sum the singular values, we can apply the Cauchy-Schwarz inequality. That is square root of the rank for the matrix times square root of the sum of the singular values squared. That is the Frobenius norm of the matrix. And the Frobenius norm of matrix also equals to like square root of sum of all the entries squared. And for every entry of this matrix, its absolute value is at most 1 plus epsilon. So we can get for each entry, it's 1 plus epsilon squared, and there are 2 to the 6n entries. Take the square root of it. And we plug what we have there for the spectral norm of the other matrix. 2 to the approximate degree, 2 to the 2n. And
Where did the 6 come from?
the total number of entries in this matrix. Because it originally it's f is from like the Boolean pool of dimension n to binary bits, and then we compose with the gadget of 6 bits. Yes. So that is just square root of a rank of m times 1 plus epsilon 2 to the 5n 2 to the minus of the approximate degree. And now we just compare the two sides, and we conclude the rank is at least 2 to the 2 times the approximate degree, and like delta minus epsilon divided by 1 plus epsilon squared. these are constant, so we can ignore it. What we get is the rank is lower bounded by exponential to the approximate degree.
Could you sum up which properties of the dual witness you used in either direction?
Yes, definitely. So so for us, like it's like the okay. So like we choose KP, this function, because it has no constant terms. And it has no constant terms that plays very well with the dual object, because the dual object has no low degree terms. And when you like compose phi with the KP function, there is only those high degree terms that gets contribute to the eigen values. And for all the eigenvalues, like the KP gadget will contribute this 2 to the minus s for all the characters. And the phi, the dual witness, they don't have low degree parts. That makes sure that this eigenvalue is small.
Okay, so you get a small norm and you use this on the right side of the board below.
Yeah.
And you didn't use anything else in the right side of the board below, right? You just used the small norm.
Yeah. So actually, so if you know like communication complexity really well, like at this point, you already can conclude just by the discrepancy method that the function f has large communication complexity. But here is for showing the approximate rank, and is for preparing for our next step.
Which properties did you use on the left side of the board?
Okay. We used the function, the dual witness has large correlation with the ordinal function f.
You use the assumption, the one that you suppose M such that the
Yeah.
use it on the right hand side, but I'm not sure that I understood how when you bounded the Frobenius.
This doesn't matter that much. I mean, the main point is like
You use it on the left.
On the left side, okay, good.
yeah, the main point is here.
Because you're gonna approximate M.
Yes, yeah, no, that makes total sense. I thought that Pei said something on the right side and I didn't understand.
Oh, and the other side, you also use it because you want to say that
The matrix M
is
is
close to
bounded.
0, 1 value, minus 1, 1 value thing. When you compute the
Oh, okay.
Frobenius norm, is
Yeah.
the worst you can get is 1 plus epsilon square for each M.
Like to bound the Frobenius, you're approximating M by M of the composition and then using the fact that the approximation is good.
Yeah, the approximation is good, and the composition is certainly plus minus 1
Yeah.
value, right?
Yeah. So we just need the entries of this matrix bounded. So like actually how well it approximate doesn't really matter.
And that's a very mild use because you're interested in the Frobenius norm and you're just using an infinity approximation. It's-
Any other questions?
I don't have direct ones, but I'm just digesting this because
Sure.
magic's
Very nice presentation so far.
I can pause a little bit longer. We didn't take any rest.
What would make you look at the inner product of the original matrix with the matrix of the dual composed with the gadgets to begin with? What does this inner product intuitively mean? Why would you?
Okay. So I think this is because if you have a polynomial instead of a matrix, that's what you will do. So when we write down the dual witness for for approximate degree, like I just write down there is this duality, but I didn't say like if you actually want to prove both sides, what you will do. If you write what you want to do, you will get something similar to this.
Okay.
So here is just to trying to imitate what's happening for polynomials.
Thanks very much.
I also think like correlation, like stuff.
But I don't think this is really correlation here. That's the best I had.
Yeah, it's not really correlation, but deal with these duality and norms. This is what plays the role of correlation, right? Inner product.
I mean, like the best scenario is we have duality just for matrix rank. We don't have, so we just lift it from polynomials and we try to do what happens in polynomials.
Okay, so the initial setting that I should have in mind is like doing the LP duality for the rank itself.
Yeah, but
Now we're doing it for the degree and the row terms, and then this is what comes up naturally.
Yeah.
This helpful. Thank you.
Okay. So now maybe let's move on. Yeah. So next is to lift for unbounded error communication complexity. Yes. So that part is maybe let's just start from like what's the due object for threshold degree. It's almost the same thing. So now the due object, if the threshold degree is greater than D, that will mean there exists a witness such that this witness, so again, we normalize it to make sure it's 1. And also, X will always agree with the function inside. So that just means the inner product between B and F is 1. And finally, B has no low degree component. So what we may want to do in the beginning is just to repeat the analysis for the randomized case. But let's see where we get stuck. So on the upper bound side, like everything should work almost. Like on the left hand, on the lower bound part is where the things break down. So so here, because f and phi has perfect correlation, what we get is like the inner product is 1 times 2 to the 5n. But on the right hand side, when we are looking for a matrix that psi represents the communication matrix, like we cannot say it's bounded by epsilon or something. So therefore, we don't have a lower bound for their inner product. That's kind of the place where we don't know how to proceed. And because of this reason, we actually don't have a generic way to lift threshold degree to psi rank. But what happens is Razborov and Sherstov, they find a relaxation. So instead of looking for like the original witness for the threshold degree, now we need a stronger witness. So we need like stronger properties for the dual object. So they call it gamma smooth dual object. So we denote it by this notation. So in addition to satisfying these properties, they need an additional property that is P is like gamma times, at least gamma times 2 to the minus n on all points. Yes, and it kind of helps there. But okay.
So does it mean degree plus or minus gamma bigger than b?
Gamma is a parameter. It just means, so this is a weird notation. This is a weird notion. It doesn't mean anything. It just means.
Oh, it is just this.
It's the definition.
Oh,
Yeah.
Yeah, it just means we have a dual witness that is stronger than the original witness.
so what's the, is this the dual to some other?
I mean, you can dualize.
Yeah.
It's the
You
dual.
can always do that.
What is that?
Uh,
Instead of
is
sine
it-
degree, but
Yeah, does it
yeah, there is that, but I'm not sure what exactly is that.
have a meaningful interpretation? It takes as a dual.
I think there is a meaning, but I just don't quite remember what exactly is that. Yeah, we will see why this smoothness helps. We will see. It will be clear. And another thing that, another technical part that will be needed, unfortunately, and it's a part that we will not explain, is the tool for analyzing psi rank, and it's due to Foster. So first, Foster is like the one to show the first explicit polynomial lower bound for unbounded error communication complexity for the inner product function. And in that work, he developed a lot of tools for analyzing psi rank. And this is one of it implicitly and in his work. And Razborov and Sherstov, they just extract that, make it explicit. So let me just write it down. What is it? It just says that if you have a matrix whose psi rank is R, then there is a matrix P that realizes this psi rank. So rank P equals to the psi rank. And also like P agrees with M inside. And finally, some analytical properties of P. The first one is all the entries in P is at most 1, and the Frobenius norm of P is exactly the size of the matrix divided by the rank and then square root. So it's difficult to explain why this is true. So let's just take it as a fact. So the psi rank of the matrix is realized by P that has every entry bounded by 1, and its Frobenius norm is exactly square root of the number of entries in the matrix divided by the rank. Right. And with these two together, we can basically try to do what happens for the approximate rank. So suppose we have a matrix M that maybe P that is given by this theorem. It realizes the psi rank of the power communication function. And then we take the inner product of this matrix with our witness. And because our witness is at this large, so it is at least gamma to the minus n times the 1 norm of P. But every entry in P is bounded by 1. So you can take it square, and that tells us it is at least gamma to the 2 to the minus n, the Frobenius norm of the matrix squared. So that's the lower bound, and the upper bound is exactly the same. The trace norm of the spectral norm of the witness and then the rank of the matrix P the probabilistic normal P, and this is 2 times 2 to the threshold degree of our function f n times 2 to the, I don't know, 5n. Wait. Times 2n. Yeah. I'm just copy runabout. And then this, we just rearrange the terms. We get rank of the function is at least URC. It will be at least gamma times 2 to the minus threshold degree of a function. So as long as gamma is some, there's no minus 2 to the threshold degree of f. So you will see as long as gamma is not too small, then the rank, the sign rank will be large. Okay. So maybe not. So maybe let's look at some applications and see how we apply these things. Especially, I guess, especially for the threshold degree. It may look very, very strange, but it actually works pretty well in a lot of scenarios. And maybe one thing that I want to comment is, like here we don't need like exactly every point is at least gamma times 2 to the minus n. Because like for the matrix rank, if you alter a few entries, you wouldn't harm the rank too much. So you can allow some of the entries to be arbitrary.
That's a comment. So I remember that this Forster theorem is related to, it's been generalized to solve this Paulson problem, which concerns like when a matrix can be put in radio isotropic position. Do you know about, anyways, might be good to know that. So it is mysterious, but I think there's a body of work in the last 5 years that
Actually, no.
yeah, kind of explains it really nice. I think a couple of years ago, I forget, somebody talked about it. Maybe it was obvious. Somebody talked about it at the seminar. Because I can give people references if they want.
Okay.
I presented it at some point as well, but I think that was to my students or something.
Folk explains P, like how to get P.
Yeah.
No, wait. Sorry, Tom. Can you say it again?
Yeah. So I was just looking it up because I don't remember the full history. But there was this open problem called an operator theory called Paulson's problem, and it was solved. It was a big open. Anyways, it was a big open problem. This question, and turned out that the solution of it turned out to have to do with when you can put something in radio isotropic position, which is basically, I think Forster did this in a special case, and then it was kind of generalized. The generalization, there's good survey papers on the different ways of doing it, and it gives more explanation for why it should be true. But I don't remember right now. But.
Okay. Yeah. Okay, so maybe let's look at some applications. Let's maybe just start from the quantum case. So it's really a simple application. You just, so like by this lifting technique, you can prove like the disjointness function. Its communication complexity for randomized model or quantum model is at least square root of n. For the randomized model, this bound was first given by Papai, Franco, Simon, and that's already somewhat non-trivial. For the quantum case, this lower bound is established by Razborov, and this is tight. It's very, very technical, but now we can just prove it in a minute. So we just take a problem whose approximate degree is square root of n. That is the n function. This is a well-known fact related to the optimality for Grover search. So we just take it as a fact here. And then we just compose it with our gadget. We know its quantum communication complexity is square root of n. And now we are basically done because I show a reduction from this function to the disjointness function. This function is just n composed with a constant size gadget, which you can express it as a constant size DNF. So the OR takes constant number of inputs. Part of it from Alice, part of it from Bob. And now for every x, like Alice can compute the OR of those x. Alice will give a new variables, and it will be like negated of those things. So the new variable xi will just be negate of the OR for, say, if here is x1 or x2, then here it would be x1, x2, for example. And we just compare it with the.
Can you write it somewhere else? I can't read there.
The
word whatever you wrote in red, I can't.
Okay.
Oh, yeah.
Okay. Yes. So yeah, sorry. So I'm just saying, like, let's say on this OR gate, it takes like x1 or x2, and then what Alice will do is just construct a new variable x prime I, and it just equals to the negation of this. And why we want to do this is exactly the disjointness function. Disjointness function is the function that says if we interpret the input to Alice and the input to Bob as the indicator vector of a set, then we want Alice and Bob to have a disjoint set. So each item I, Alice and Bob, one of Alice or Bob should not have that item. Yeah, so after, so from this left side, which corresponds to the lifted function for n, and on the right hand side is a disjointness function. So by constructing in this way, we reduce the lifted function to the disjointness function. Therefore, if disjointness function is simple, then the lifted function is simple. That's one application. Okay. Another application that actually there are a lot of applications I want to show, but let me just decide that the other application that I want to show is the following result. It says that for the communication complexity case, the pi2 and sigma2 complexity class is not contained in the unbounded error communication complexity. Classically, so unbounded error communication complexity corresponds to the PP complexity class. And classically, we have total theorem, which says the polynomial hierarchy is contained in P to the PP. So people may think that sigma 2 and pi 2 is contained in PP classically, but of course we don't know. And here for the communication complexity, this is not the case.
This is conditional, right? It's still conditional P different than P.
No, this is for communication complexity. There's no condition, it's unconditional.
Oh, okay.
High-level reason for the difference that we're not accounting for computing power here? Is the high-level reason for the difference we're not accounting for running time or other resources?
So a lot of things are different in communication model than classically, right? Yep. Like here we know P is not equal to BPP. There is separation between deterministic and randomized communication, and like we know, so a lot of things we know, but classically we don't know. Yeah, so other than that, I'm not sure how to explain. Yeah, okay, so maybe I just, maybe I won't show you the proof. I just tell you what happens here. So here what happens is that we have this function n composed with the OR function. But n takes like m inputs, or takes m square inputs. And you can show that its threshold degree, even if you require that smoothness condition, is at least m. So the proof is actually also very short, but it's a bit technical to explain, so let's don't do it maybe. And then you see we can just compose this function with our gadget. It has large unbounded error communication complexity. Okay, so maybe now I need to explain what is pi2 and sigma 2 for communication model. So maybe it's good to just start from what is non-deterministic communication protocol. It's just like so some witness that some certificates that shows that your input is a 1, and which we normally use a rectangle. So the MP is just the function that can be represented by disjunction of 2 to the polylog n number of rectangles. And a typical example is the intersection problem, just the complement of the disjointness problem. Alice and Bob, they have a indicator vector indicating a set. And you want to know whether Alice and Bob, they share any input. And then in this case, like for each element, it corresponds to a rectangle. That is xi and yi. So this is empty. And Pi2 is just take another layer by taking the n function. So it's just and composed with or, and in the end, it's just a rectangle. This is Pi2. And all the gates takes at most polylogarithmic 2 to the polylogarithmic number of inputs. Okay, so this is NP and this is Pi2, and the co-NP is just the complement of NP, and the sigma 2 is just complement of Pi2. Okay, and now I think it's pretty clear that this function and or, right, it looks very like a function that can be computed in Pi2 because it's and composed with or composed with a constant size gadget, which you can express as a DNF. And the two layers of the OR gadget were be compressed into one layer. And in the end, it's AND gadget, and the AND gadget just corresponds to a rectangle here. So this function is contained in Pi2, but it has large unbounded-error communication complexity. Yeah. So another of the final application I want to show is circuits complexity. Like there is, so here the kind of circuits is a threshold circuits. What I mean is like a threshold circuits is like a gate is just a threshold function. Like you have input x1, x2, x3, x4, and then you can evaluate it like arbitrarily some weights ai, xi, and ask whether it's greater than some value or smaller than some value. And if that's the case, it's output 1. If that's not the case, output 0. So that's a threshold gate. And here we will be interested in like depth 2 threshold circuits. And each threshold circuits will take at most polynomial number of inputs. And the question is like, what's the relationship between a threshold, depth 2 threshold circuits and a threshold circuits composed with majority? So majority is like a special case of threshold circuits where the weights are all 1. And the relationship between majority composed with threshold, and the majority composed with majority. So surprisingly, like these two are equal. So the two layers of majority gates just equals to a majority composed with threshold circuits. So this is like classical results due to Goldman.
After polynomial over. That's right.
That I mean, like we are but if we are talking about the complexity classes, it's the same. Hashtag and Razborov. And then the other classes, like the containment is obvious, but whether they are equal or not, so the result is they are not. And both these separation can come from like lifting. The first one, yes. The first one is like the majority is not does not equal to threshold majority. And why this is the case, this is a result due to Berman and the Wolf. And just consider the function which is called odd max bit. Odd max bit is just the following function. It outputs 1 if you look at its input like from left to right and look at its first 1. If the first 1 appears on the odd bit, then that's 1. And 0 otherwise. So there is a very easy, very simple linear threshold function to compute the odd max bit. It's like 2 to the n times x1 minus 2 to the n minus 1 x2 plus 2 to the n minus 2 x3 and etc. Yeah. So this thing is contained in it can be computed by a threshold circuit. And there is this classical result due to a Beagle. It says this thing has approximate degree square root of n. And therefore, if you compose with the function with this gadget, we will express this gadget as a CNF, as a DNF. So we will write it as like odd max bit composed with or composed with and. And it's not hard to see that the OR gate can be absorbed into the odd max bit. So this thing is a sub function of the odd max bit, the original odd max bit. So what we get is odd max bit composed with the AND function. And this thing will have large randomized communication complexity. In fact, you can show that its discrepancy is very, very small. Less than like 2 to the square root of it. And so odd max bit composed with AND function is clearly contained in threshold gate composed with majority gate, because to compute AND function, you can just add some 1 to the majority gate, add some 0 to the majority gate. But on the other hand, if a function can be computed by majority composed with majority, then its discrepancy will actually be large. Here its discrepancy is small. So that shows this function is not in majority gate, but it's in threshold majority gate. So this is the
Shartulo result are you using to assert that the discrepancy of OMB composed with a gadget is small? You said the discrepancy of the composed function is small.
Yes.
Which result or tool, like?
Because at some point we analyzed the spectrum norm of the function. We actually didn't directly say it, but the spectrum norm will be related to the matrix discrepancy. Right. Yeah. So clearly here I'm saying something I didn't explain very well in the previous part, because I don't want to define discrepancy. Yeah. Okay. And for the final part, I can just take a function that is like odd max bit composed with a quality function. And here I will be cheating a lot. Here I will be cheating a lot. So first, this function is contained in threshold circuits. This is because for the equality function, you would just write it as like greater than whether x is greater than or equal to y, plus whether y is greater than or equal to x, and minus 1. So when they are equal, this is 1. When they are not equal, this is 0. And then just plug in, and greater than can be computed by a threshold circuit gate. So just plugging these things into each variables, and then you get a threshold composed with threshold circuit. So that shows this direction. And the other direction is what I'm like really cheating. So odd max bit, you can write it as composed with equality is just odd max bit composed with the AND function, and then composed with the XOR function. Right. And then if you look at like the function lifted, that is odd max bit composed with if you look at odd max bit composed with the AND function, composed with the gadget, then what you get is odd max width composed with and composed with like or. So composed with parity. And this is a constant size or. Other than that, everything is fine. And also we have, it's actually not hard to show the threshold degree for this function, the odd max fit composed with the n function. Maybe it's like n, maybe it's n cube, I don't, maybe it's n cube, and here it's like 2 to the minus. This that is greater than. Therefore, its unbounded-error communication complexity is large. And what's the point? So if a function has, if a function can be computed by threshold composed with majority circuits, then its unbounded-error communication complexity will actually be low, because what Alice and Bob can do is they just pick based on the weight on the while, a gate for the majority. And then Alice and Bob can just compute the majority, the output for the majority gate by exchanging the number of ones, which is logarithmic. Yeah. Okay, so this result is due to like Monday, Calabati and Monday. So I think that's all I want to say. Thank you.
Thank you.
Thank you for staying. Any questions?
I'll just point out that there's lots of other applications, like in learning theory, there's lots of the same thing.
Yes, I want to keep it a complexity.
Yeah, for sure. Yeah. It's a good hammer. Very good. Thanks again.